So we will continue. We got the Rayleigh's formula, and what we understood is at higher frequencies the Rayleigh's formula is wrong, and that discrepancy that we got is ultraviolet catastrophe. Now this issue taken by Planck, and he gave the Planck radiation formula. Planck radiation formula. Actually, it has a small difference what he took. Instead of taking the classical notion by Rayleigh on the average energy, Einstein took a little bit different approach, and he got a very good result that is observed by the experiments. So actually, Planck he used he applied the Bose-Einstein distribution function, and also another thing he took in consideration. The oscillators in the cavity that doesn't have a continuous energy E or epsilon, but it takes certain specific values of energies that he called as the quanta, the photon, quanta of energy, that is called the photon, and it has an H. Okay, and this is the difference between the approach by Rayleigh and Planck. Rayleigh they just moved classically, and they made the classical approach, but Planck, what he did, he used the Bose-Einstein distribution function, and he told the oscillators in the cavity that doesn't possess all the continuous energy epsilon, but certain specific value of energies only these oscillators are taking. So that made a huge difference between this Rayleigh and Planck formula. So instead of considering that continuous energy, Planck told the oscillators in the cavity that take certain energies, that is epsilon is equal to n h nu, where n is equal to 0, 1, 2, etc. So all these values. Okay. And the second thing, an oscillator emits radiations of frequency nu when it drops from a certain energy levels to the another. Okay, like the transition between what is called energy. For example, it has an energy, for example, epsilon 2, and this level has an energy epsilon 1. Then when this is dropping from this energy level to this energy level, then there is a emission of there is a radiation that comes out, emits, and this radiation has the energy of the suppression of these two levels. So the things are discrete now. Instead of having a continuous spectra, you have a discrete spectra, and this each discrete bundle of energy h nu, what you are putting outside, that is called what is called a quanta, the photon, the quanta of photons, and this has a behavior like a bundle. Okay, it is like a single entity, quanta of photons. Okay, so that is the difference. And this oscillator energies, that is limited to an h nu, and the average energy per oscillator on the cavity walls, you can write it using your Bose-Einstein distribution function. That is epsilon average is equal to h nu by e raised to minus epsilon by kBt. Instead of epsilon, I am using h nu by kBt minus 1. So this is the what is called Bose-Einstein distribution function, because you know f of nu is equal to 1 by e raised to alpha e raised to epsilon by kBt minus 1. That was the distribution function for the bosons. And now the average energy means you have to multiply with energy, and your energy epsilon is h nu. Okay, n is nu, if you take the first n is equal to 1, then you have n h nu. So this is the average energy you have to consider instead of kBt that we have used in the Rayleigh-Jeans formula, where you are completely using the classical approach. Now the Planck's radiation formula, that we will get it as the u nu d nu is equal to E average G nu d nu. Okay, and you already have a G nu d nu, and what you need to multiply with the average energy. Instead of kT, you are using this one. So that is the difference. That will make a huge difference. So 8 pi h by c cube h nu divided by sorry, h already taken. You already have a nu square, and then now you multiply with the nu cube d nu divided by e raised to h nu by kBt minus 1. So this is called Planck's radiation formula. Planck's radiation formula. Now the things are more clear, and which is very much agrees with the experimental findings or the observed black body radiation spectrum. Okay, under the thermal equilibrium, the energy distribution can be determined by the Bose-Einstein statistics, and that is an important thing. And there is an important difference between the photons and other particles. That is, the number of photons in a cavity need not be conserved. Unlike the gas molecules or electrons, photons are created and destroyed all the times. And although the total radiation energy in a cavity at a given temperature remains constant, and the number of photons that is incorporated, this energy can be changed, and the non-conservation of energy or the photons means that your alpha equal to 0, hence Bose-Einstein distribution function become this one, because here alpha you taken it as 0. Okay, so that is because of the non-conservation of photons, because photons are always created and destroyed, so you cannot say this is conserved in a cavity. So you have to take alpha is equal to 0 because of this non-conservation. So this is the what is called, so before writing this actually here, therefore epsilon you take it as 1 by e raised to h nu by kBt minus 1, because here e raised to alpha, this alpha you are taking it as equal to 0 because of this non-conservation. That is why you are getting this. And the number of independent standing waves per unit volume in the frequency interval nu and nu plus nu d nu is given by our previous equation that we derived, and the energy density of radiation in the frequency range nu and nu plus d nu is given by this. Okay, so you are getting the Planck's radiation formula. Okay, so you just very well study these things, both the Rayleigh formula and Planck radiation formula that will be useful somewhere else, either in exam or in the entrance exams. So you just understand the concept and study very well.